Can y'all see? Is this still not working? Dang it! I can't remember what I did last time, but anyway. So we're going to bring some type of AC source into this side over here. And what do we call these capacitors right here? What's the function of these two capacitors right there? What's the function of C1 and C2? Huh? Technically, yeah, but huh? Capacitors can't convert AC to DC, and they can't convert AC to DC. We have to do that electronically. So we have power supplies that convert AC to DC. So capacitors can't do that. One thing is they change their opposition with frequency. So we're using pretty good sized capacitors. What we do here is one thing that's very important is a capacitor will block DC and pass AC. Now this is dependent on the frequency. So if I'm using a 100 microfarad capacitor right here, and we're bringing 1,000 hertz in, 1 kilohertz in, and X of C would be equal to 1 over 3.28 times 1,000 times 100 microfarad. 100 microfarad, Rich. We leave off the farads, right? So if I was to calculate that, if my don't kick off my display again, I keep getting my thing. Then I'll do the math for you just to get a feel. So this is the 3.28. Oops. 3.0. 3.28 times 1,000 times 100 times 10 to the minus 6. Then we take the reciprocal of that. Oh, here it is. And that thing would only have 3 ohms worth of resistance or reactance. So technically, if we choose the right size capacitor, we just ignore it. It lets the AC pass through it just like it's not there. So 3 ohms relative to what 1.7K over here on the right hand side, it's nothing. Especially when we start dealing with all the resistance. Now, if I'd used a picofarad capacitor, so on all your amplifiers, you're going to see these capacitors up in the microfarad range. 3 ohms worth of opposition. But the problem is that a DC source, and I showed y'all this the other day, sees an AC signal as a short circuit. So I've got to have some way to bring an AC signal into my circuit and not affect the bias. So what was the bias we calculated on circuit 3? VR2. VR2, we calculated it to be circuit 3, Rich. So that 1.5 volts is there, and what happens is when I bring an AC signal, this allows the AC signal to go through, and then what happens, it don't let the DC get out, but now it brings the AC in. And then what the AC is going to do now, it's going to subtract from the 1.5 volts or add to the 1.5 volts. So it's going to be like DC sources in series, right? You understand? So if this is 1 volt peak to peak, then that means when this came up, then when on the positive alternation, this would go up to it would go up to 200 2 volts, and on the negative alternation, it would go down to 1 volt. And if we so the temperature is not changing this voltage. The input resistance is, the input signal is changing that voltage. So what that capacitor does, it allows us to get what? Allows us to bring AC into a DC circuit without affecting either one, without creating a short circuit. Now the problem over here, this is not AC right there, that's DC. So this thing's got a gain of 5, so that means over here, if I'm putting 1 volt peak to peak in, then it's going to go up to 5 volts peak to peak out, right? But I need to redraw that because it's going to be opposite. But the problem is this 5 volts peak to peak right there is riding on this 5 volts. So on the output, we got this thing setting at 5.watt, around 5 volts, right? And this AC is riding on, and here's 0 volts down here. This AC is causing this to happen. It's going down 2.5 volts this way and going up 2.5 volts that way. That makes sense. So this is not AC either. But when I couple this out, we want to get AC. So I want to strip off this bias voltage right there and let the AC go out. So on this other side of this capacitor, what we would have, this would be 0. What we would actually have is we'd have an AC signal coming out. So these capacitors, C1 and C2, these are called coupling capacitors. Because what does it do? It allows us to couple an AC signal in to a DC circuit. It allows us to couple a DC signal out of and turn it back into AC, right? You understand? So that's the function of those capacitors. If I remove this guy, I wouldn't be getting AC out anymore. I'd be getting DC changing at AC rate. If I left that coupling capacitor out right here, this bias voltage would drop down to about 0 volts. Because the DC sees an AC source as a short circuit, and an AC signal sees a DC source as a short circuit. So that's why when we say the signal flow, when the signal flow comes in, what does it do? It comes up here and splits because this sees this as a what? The DC signal sees that as a common. It don't see that DC power supply, and it goes this way. And it goes that way. And that's what your AC signal sees. Now, what happens is every amplifier is going to go into a load. This right here is an unloaded amplifier. This is our load right there, but that's not doing anything for me. So what we're going to have to do is we're going to have to come up here and we're going to have to hook some type of load over here. And right now what we're going to do is we're just going to assume it's a resistor. Because resistors, we understand resistors, and they're easy to work with. So if I load the amplifier, would you expect the output to go up, or would you expect the output to go down? You'd expect it to go down. That's good. I mean, it's just like your car battery out there. If your engine's not running, go out there and put a voltmeter across your car battery and turn on your lights and everything. What do you think the voltage is going to do? It's going to do what? It's going down because it's not a regulated power supply. So what happens if I made this a 10K? My load right there is a 10K. Well, what this would do is this is going to be my input resistance circuit. So Rn is going to come up here. It's going to come in here, so this will be my input circuit. It's going to be what? It's going to be a 10K, which in this situation, a 10K in parallel with a what? With a 1.8K. In parallel with sorry, 200 ohm times beta. And we just choose a beta. Since beta can be over such a range, we just choose something in the center. Now my output is being developed right here. So my output circuit sees this right here. It sees R3, which is 1K, in parallel with a load resistor, which is 10K. So what would my R out be? So what we're doing is we're taking the 1K, which is R3, we're putting it in parallel with, we'll call this RL. So what would R out be? 10K in parallel with a 1K. I know it's going to be less than what? 1K. Let's go ahead and calculate it out. It's going to be right around, looks like around 900 something ohms, or 800 something ohms. So two resistors, you got two formulas available. You got the product over the sum, and you got the reciprocal formula. I like to use the reciprocal formula because it works all the time, no matter what your circuits are. So R out would be equal to 1 over 1K plus 1 over 10K. Anybody got it yet? So the actual formula, if you look at your formula sheet, then your gain, your AV for a common emitter should be R out over RE. That's one formula. So we said we had a gain of 5, but it's actually a gain of 990 over 200. So right off the bat, if you hook up a load to the amplifier, you should expect the gain to go down, which means the output goes down. So what we got now, it's not exactly 5, but it's 4 point something. And what I did, guys, we have a rule called the we have a rule called the 10-to-1 rule. In a parallel circuit, if one resistor is 10 times greater than this one, then normally for getting an approximation, you can ignore the big one. And it turned out pretty close, right? It's called what we call the 10-1. So in a series circuit, if you've got two resistors in series and one is 10 times greater than the other, then for approximation, you can ignore the little one. On a parallel circuit, if one is 10 times greater, we ignore the big one, right? Everything's opposite. So when we hook up when we do lab 34 and we hook up and we calculate the gain, we're going to have to use this R out instead of using what? Instead of using just RC. Are we okay? Okay. So what we're going to do, and hopefully the other guys can get this. By the way, if you see the guys that's absent, they can submit the worksheet by scanning it or taking a picture of it and making a copy of it. I'll text them. That's in the, I think that's actually in the syllabus. You got your worksheet, Bernard? Okay, let me see it. Okay, so the first lab we're going to do, everybody needs to get their lab book, because we're going to do lab number 33. We'll try to do 2 labs. We'll try to do 33 and 34. make sure we're looking at the same circuit. So I had to modify mine a little bit. I'm using a fixed power supply over here. So I'm using the plus 5 volt supply. And then I'm going to bring this to a 10K pot. And then I'm bringing this into my base. And we're calling this R1. And it's 33K, right? And then I'm bringing this into my transistor, which is a 2N3904, which is a NPN, I'm sorry. And then we're going to a 100 ohm resistor. And they're calling this R2. And then I'm bringing this over to the positive variable supply on the trainer. And this is variable. So what we're going to do, if you look at the chart, is first of all, we're going to set up a base current. So the first base current we're going to use is 50 microamps. And then the second one we're going to do is 100 microamps. And then the third one we're going to do is 150 microamps. So what we're going to do, of course, is we're not going to put a current meter. We have a nice little resistor right here that I can calculate my current, right? You understand? So what we can do is we can measure the voltage drop across that resistor. So a lot of times you don't have to use an amp meter to get current, right? You understand that? We've got a resistor that's in series with the base current, so we can calculate IB. So IB is going to be equal to VB divided by 33K, but that's not what we need. We need to calculate VR1 to give me those, right? So VR1, which would be voltage drop across R1. What do I need? What VR1 do I need to get 50 microamps? Using Ohm's law, V is equal to what? I times R. What size is this? 33K. So the first one we're trying to get is 50. The first one we're trying to get is 50 microamps. I'm gonna multiply that by 33K, and this will tell me what I need to get that resistor to drop. So this will be for, we'll call this I1, and we'll call this I2, and we'll call this I3. So I1, what voltage do we need? And then VR for I2, this will be 100 microamps times 33K. Should be twice 1.62, right? 1.65. What we got? What's that? For VR1, we've already got 1.65. We're working on I2. For VR1 for I2. And then VR1 for I3. VR1 would be equal to 150 microamps times 33K. What does it give us? That's going to be close. I might have to run this off the plus 12 volt supply. We'll see that. We might have to switch it over because I'm using the 5 volt supply. In fact, let's go ahead and do that already. Oh, we are running it off. I am running it off the 12 volt supply, so we're fine. That's good. So this is the plus 12 volt supply, so we should be fine. We're supposed to. I might have my. I don't know where it's at. I'm supposed to have a blue one in here. Here it is. I don't need that. You keep that. I mean, all I knew. Okay, then when we get over here, we're going to have to calculate IC. How can I calculate IC without measuring it? We're going to have to do this several times, but it's going to be fairly easy. How can I calculate IC without measuring it? So how can I calculate IC without actually breaking the circuit and measuring it? Huh? No, collector current is here. We don't worry about it. This is collector current right there. I've got a 100 ohm resistor in series with IC. So all IC flows through the 100 ohm. So what we can do is we can measure the voltage across the 100 ohm to get IC, right? Understand that? So for what formula would I use to calculate IC? We're going to have to do this several times because notice your voltage collector to emitter now is going to be the voltage collector to emitter, and then it says IC. Y'all see in the chart what I'm talking about? So how am I going to calculate IC for each one of these voltages? So IC is going to be equal to what? I is equal to what? Yeah. So I'll calculate VR. I'll measure VR3, and then I will divide that by 100. $10 milliamps per volt. So this is 100 ohms is 10 milliamps per volt. Are we okay? So we're about ready? Huh? So what you need to know? VR3 is given. Well, no, we measure VR3. We don't calculate VR3. I got my voltmeter up here. So what I'm going to do is I'm going to measure VR3. I hadn't measured it yet because we hadn't hooked the circuit up yet. So I'm going to come over here and I'm going to put 50 microamps of base current in. Then what I'm going to do is I'm going to go over here and I'm going to put voltage collector emitter 2 volts, voltage collector emitter 4 volts, voltage collector emitter 6 volts, voltage collector emitter 12 volts. And then I'm going to measure the voltage across, when I set voltage to collector to emitter, right, you understand, then I'm going to measure the voltage across R2. Once I get the voltage to collector to emitter to where they say that I need it, right, you understand that? So if I set this right here to 2 volts, how much voltage is R2 dropping? I have no idea unless I do what? And I measure it. So I'm going to measure this. So I'm going to measure it at 2 volts, collector to emitter. I'm going to measure it at what? I'm going to measure it at 4 volts. I'm going to measure it at 6 volts. I'm going to measure it at 8 volts. And then over here on the right-hand side, I'm going to do my little bit of math, right? You understand? And over there where it says IC, I'm going to record those values. That makes sense now, Austin? Yeah. So No, I'm looking down the light. I'm looking down voltage collector to emitter. I'm looking down voltage collector to emitter. You see that in the chart? It says, and look at the rate. It says 2 volts, 4 volts, 6 volts, 8 volts. What do you mean 12? I got 12 volts right there. We're over on this side right here. And this is a watt. That's a variable power supply. So you're looking at the 12 volts over here. That's what I do have over here. But I'm going to come over here and adjust this until I make this thing measure what? Until I make this measure, this resistor right here, I'm going to measure this, and I'm going to make it start off, I'm going to make it measure 1.65 volts. When the 33K measures 1.65 volts, how much base current do I have? I have 50. Then what I'm going to do is I'm going to start adjusting this power supply right here until I measure what across here? 2 volts. After I measure 2 volts there, then I'm going to measure the voltage drop across R2. Then I'm going to plug that into this formula, and I'm going to use that to calculate what? IC. Understand now? IC. What's I equal to? What's the formula for IC? What's the formula for current? Excuse me. Ohm's law. Okay, so here's R2. Collector current flows through R2. So my formula for IC is going to be VR2 divided by, what size is that? 100 ohms. So that's this formula over here on the right-hand side. And I need to make me a line down here. So we okay so far? Okay. Okay, so I'm going to come over here. The first thing I'm going to do is I'm going to set my base current. So I got my voltmeter here. Where do I need to measure to set my base current? Put my wire pulled out. What do I need to measure to, here's my 100 ohm. It's in the collector. I have my 1,000 ohm. Sorry, the 300K, 33K, I'm sorry, hooked up to the base. Here's my wiper off my pot, which you can't see, but this is coming down here. And here is R1 and here's R2. So this is 100 ohm. So what do I need to do? Where do I need to measure the 1.65 volts back? Across the 33K. The 33K is setting the base current flows through the 33K. So here's our base current right here. The base current is flowing here. Right? You understand? So if the base current is flowing there, I can measure the voltage drop across R1 and use that to calculate the base current. So what I'm going to do is I'm going to put my meter across R1, which is the 33K, and I'm going to adjust it till I get watt across it. 1.5 volts. 1.65 volts. Dang it. So here's R1. This is the 33K, right? What color code is 33K? Orange, orange, orange. Good. So that's about the best I can do, guys. So we've got about 1.65 volts across this, right? Okay. Then what am I going to do is I'm going to move over to the collector to emitter. And I'm going to adjust this until I get 2 volts dropped across it. Something's not working. Okay, we got it now. I just didn't have a good measurement. Adjust my 12 volt supply until I get 2 volts across it. Okay, that's about the best I can do. And then I'll measure across my 100 ohm resistor. And it's dropping 900 volts. Yeah, let me see what's going on. Drop my scale down. I don't know what happened. My meter keeps turning off my train. The way I have to set my meter. Let me double check. Here's input. I need to come up with a method so my meter don't keep turning off my trainer. Somehow I pull my transistor out. So let's double check this. So this is across my 33K. A little bit, right? Whew. That's good. I've got my voltage collector to emitter. Hopefully it's still at 2 volts. It's a little high now. And then across my resistance. So we have 4.7 or 5 millivolts across my collector resistor. So what would be my current? Yeah, 5 millivolts, 4.7, 5 millivolts. What's that? I thought I did too, but this is, so here's across my base resistor. We have 0.63 volts. Here's my emitter to collector voltage. We're supposed to have 2 volts. Okay. And this is across the 100 ohm right here. So that's 5 millivolts. So what would I see there? Oh, 50 microamps. Yeah. Okay. No, VR2. Oh, VR2. Yeah, you're right. It's measuring four. VR2, which is the 100 ohm, was measuring 4.7 millivolts or 5 millivolts. Okay, what do I need to do next? You can calculate your IC, right? Everybody got that? Okay. What we come up with? 500 microamps, 50 microamps. Okay, so I'm gonna go back to my voltage collector to emitter, and I'm gonna set voltage collector to emitter. I'm gonna set this to what's next? 4 volts. I'm gonna come back and double check my base because we got to make sure this stays the same. It said no, it's good. Okay. So this base current had changed. I'm gonna come over here and I'm gonna look at I want my 100 ohm resistor and it's dropping 5 millivolts. So the notice the current stayed what? The same, right? Everybody okay? Everybody okay? Ready to move on? We got 500 microamps both times so far. Go ahead. What are you saying? Yeah, but we're recording in 33-2. So we did the 2 votes. We did the 2 votes, right? VR2 was so the first one it was 5 millivolts. This was basically still what? 5 millivolts, right? Now we're going to go to 6 volts. Everybody okay? So here comes 6 volts. We should see this vary just slightly. So there's 6 volts, close enough to it. Double check my base current. Still should be 1.6. See, the base current is saying what? Saying the same, right? That's really good. Okay, so here's VR. This is VR2. So now it's measuring about 7 millivolts. Excuse me. No, we're on 6. We're not to 8 yet. We're just now on 6. So VR2 is 6.6 millivolts or 7, so about 700 microamps, right? I mean, I'm sorry, 70 microamps. I keep going one over. Are we okay? Move on. Okay, so next we're going to shoot for 8 volts. And that's the best we can do. So 8 volts. So let's write that down. 6 point. We'll use 8 volts because we're just going to demonstrate. So this is 8 volts. That's the best we can do with this power supply, guys. Here's VR. It's 1.6, right? 1.65 or 1.6. Something is going wrong. I had a wire pull out. So this is let's see. So the voltage collector to emitter is measured 7.5 volts, and that's the best we can do, right? I want to come over to my resistor, so something don't make sense. See what I'm talking about? Yes or no? So I'm trying to figure out what's going on here. So here we have okay. Now I thought we could get 12 volts out of this, but we're getting 17 volts out of here. So here's my voltage collector to emitter. We can't get 8 volts, right? Okay. And I'm gonna come over here and look across this resistor now. Okay. It's measuring 10 volts. So my base current is gone wild, right? You gotta be real careful because the transistor's going. Yeah. The transistor was getting real hot because the current, what was the current? What current y'all got? No, let me turn it back. Let me turn it back up. Right. I'm sorry. So the best we can do is 7.4, and then the resistor is dropping. Can y'all see that? 11.7 volts. And I'm gonna turn this down real quick. So how much current would that be? I can't. So what was having is so voltage collector's emitter was equal to what? Then 7.6 volts is what we got. And what was my IC? 100 watt. So how much power was my transistor trying to dissipate? It's dropping 7.6 volts. It's got 120 milliamps flowing through it. So what's the power my transistor is trying to dissipate? What's it rated at? So that's why I turned it off real fast, guys. And we'll have to keep an eye on that high voltage thing right there. So it's rated at 200 milliamps, but it looks like we didn't exceed that. But when we look down here at the power rating, it's only rated at what? Well, we should have been okay. It's supposed to be rated at, what did we come up with? 700? Yeah, so we're about 300 milliwatts over. So you got to look at two things. In what region are we operating in? We're operating in the active region, right? So in your data sheets, this tells you the maximum current you can get out of it if you saturate the transistor. In the active region, we're not using this. We're normally down into here. So this is why I turned it off real fast, because it's only rated at 625 milliwatts, and we were trying to make it get what? 900, yeah. It was getting warm. So. Okay, so now we can move on to the next one, right? And we'll just be careful on that last one. So we're gonna go up to 100 microamps of base current. So it means the transistor is going to move towards saturation. So we should expect RC to drop a little more voltage, right? Okay, so here we go. So what do we need to cross the What do we need to cross R1 to get 100 microamps? 3.3. Okay. Dude, wrong way, Rich. Ooh, that's not bad. Then I need to come over here and I need to set my voltage selector to emitter. We start off with 2 volts. Oops, no, that's good. Here's my voltage across my so we got 14 millivolts across there. And this is VR, this is VR2. Yeah. So we're over in the second 2 columns under 100 microamps, right? Okay. Okay. And then we're going to, so this is 2 volts, collector to emitter. We okay? Everybody okay? So now we're going to move votes. Okay, that's 4 votes. What should be across on 3.1? 3.35, close to that. Okay, this is 4. This is voltage VR2. It's measuring 15.5 millivolts. We okay? Everybody okay? We're going to go to watt. 6 volts. So here's 6 volts. Check my base current. 3.3. Here's the R2. 21.21 millivolts. Are we okay? We're going to try to go to 8 volts as close as we can get it. So that's the best we can do. That's 7.4. We'll just use that as a. It's dropping 11.65. Okay, so that's the second column, right? Second 2 columns. By the way, y'all can just record VR2 and y'all can come back later on and do the math, right? Okay, so now we're going to increase our base current to watt, 150 microamps. I need across R1 about 5 volts. Wrong way, Rich. That looks good, guys. 2 volts. All right. VR2 measures 26 millivolts. We okay? I'm going to go to 4 volts. Voltage emitter. I'm going to get me a wire. Don't need it. We done 2, but we done 2 volts, right? Okay. Need to set it to 4 volts, right? Good. VR2. 28.6 millivolts. Then we're going to go to 4 volts. I'm sorry, 6 volts. VR2 is equal to 41.6 millivolts. And what's the last one? We can't leave it on that one very long, right? And it's measuring 11.7 millivolts. So let's double check. So 50 microamps, what did we get for 2 volts? VR2. 4 volts, 6 volts, 8 volts. Okay. What current do we get for 2 volts? Have y'all got them calculated yet? We're just going back double checking our. We're double checking our. Huh? 50 microwatt, right? First of all, we did VR2. Now we're going back and seeing what we got on IC, right? So 2 volts for IC, 4 volts for IC, 6 volts for IC, and then 8 volts for IC. 100 and something, right? Okay. Now 100 microamps base current. What did we get for 2 volts VR2? 14 milli, 4 volts, 15.5. We okay? 6 volts, and then 8 volts. Yeah, we're moving towards saturation, that's for sure. IC for 2 volts, 140 micro. IC for 4 volts. IC for 6 volts. IC for 8 volts. Yeah. I'm moving to 150 microamps, 2 volts VR2. 4 volts, 6 volts, and then 8 volts. Yeah, okay, so IC for 150 micro, what did y'all get? 2 volts, 4 volts, 6 volts, and then 8 volts. This at home, because we've made everything that you need to do, is these are referred to as collector characteristics curves. And if you look at your chart, down at the bottom, you got VC is equal to 1 volt, which we didn't do. We did what? 2, 4, 6, and 8. Everybody see that across the bottom? Up the left-hand side, this is where you're going to put your ICs at. Basically, what we do is we just start at the, I don't know if we should do the maximum or set it off for maybe 6 volts. But what you can see, you can actually see this happen, is that for a certain voltage collector to emitter, for a certain base current, this line right here, it's not exactly flat. It just goes just goes a little bit. But then when you exceed that rate, can you see what happens on the right-hand side over here? That sucker just did what? It just took off. So this happened when we got up to around what? When we tried to get 8 volts. That's when it actually took off. So your characteristics curve, so this would be IB. So what's our first IB? 50 microamps. And then our second IB would be 100 microamps. So you're only going to have 3 lines. And our third IB would be 150 micro. Everybody understand that? And then what we would do, we'd say, okay, at 2 volts, which would be 2, 4, 6, 8. What did we have? And this would be IC would be what's our lowest IC? Yeah, so we're probably going to set this off in microamps, maybe 50 like this, maybe 25, I don't know. And then so if this was 50 microamps, then my first spot would be right there. And the next one would be right here. But what you see on the next one, it slants up just what? Just a little bit. And then we went to 8 volts, it did what? It took off. And these are called characteristics curves. So basically we're trying to show that when we set a certain base current, right, that collector current doesn't change hardly anything for a base current. So what we're doing is basically proving beta. But it's not exact, right? You understand that? So your curve should have a what? A slight slant until you get to 8 volts voltage collector to emitter, and we've exceeded what the transistor would do. Now, of course, we had to turn it off real fast because we saw that the transistor was conducting about, it was producing almost 900 milliwatts of power, right? So I cut it off real fast. So y'all know what y'all going to do on table 33-1. Are you okay? And you should end up a chart that looks something like what? Something like this, but instead of having all these lines, you're only going to have what? 3. Are we okay? Okay. And then over here on the next chart, you're going to figure out what it would be for voltages that we didn't measure. Y'all understand how you're going to do that? Your 3 volts and 5 volts. We didn't do 3 volts. We did 5 volts. But what I can do on this curve is I can say, okay, if this is 2 volts, 3 volts will be up there. I should be able to draw a line up there, right? Does that make sense? And then come over here and anticipate what it would be. That makes sense? Okay. Does the experiment indicate that beta DC stays constant? No, it don't. It's approximately constant, right? You understand that? It's not exact, but so don't forget your conclusions, guys, when you answer these questions. We've had some turned in. People didn't write a conclusion, and it's a conclusion about what you learned about the lab, right? And then answer these questions. Since we did the circuit and everything in class, these questions in your chart are going to be graded heavy because I did the circuit, right? You understand that? Okay. I'll take a 10-minute break, and we'll come back and do lab 34.